Hello everyone. I'm going to discuss section 5.3 cache performance and also review one homework exercise question today. Another repeat of the cache organization. CPU is given a memory address A3. The last 4 bit is a block offset. The following 2 bit is a block index and tag value. Using the block index, you go to the cache, you get the tag value, compare it with the tag value from the memory address. If it is not a match, that's a cache miss. Upon a cache miss, CPU is going to go to the main memory to read that block and copy into the cache, as well as changes the value, tag value in that corresponding to that block. Another discussion we did last time was a write operation. CPU is executing stored instruction. The D0 to DF, the corresponding block, is already in the cache, so this is a cache hit. On the other hand, this is a write operation. So the write-through policy is that you not only update the value in the cache, since it is a write operation, also update the value in the main memory. So main memory changes, main memory access, it takes 100 cycles. So although it is a cache hit, you still need to consume 100 cycles to reflect the changes in the main memory. So that's a disadvantage of the write-through policy. Alternative idea is called the write-back policy, which means that you just make a changes on the cache. That change is going to be reflected into the main memory only when that particular block in the cache is being replaced in the future. So for that matter, the system has to remember whether the block has been updated or just a clean copy. We need a 30-bit for individual blocks. So this is one of the quiz question. Memory access pattern D6, D8, DE78, 7078. The D6 is going to be a cache miss, but once that block is brought into the cache, which is a green color, and then the following two memory accesses, D8, DE, is going to be a cache hit because it's already there. 78 is a cache miss, but it will bring into the cache, and the following two memory accesses is going to be cache hit. So altogether, hit ratio is 4/6 or 67%. We also talk about the cache performance depending on the cache size as well as the block size. If you increase the cache size, miss rate decreases. And if you increase the block size, miss rate decreases because you have a better chance to exploit the locality of reference. Block size is larger, which means that whenever there is a cache miss, you are bringing larger size of the data from the main memory to the cache, and the future references are around the neighborhood, then you can be better off. The miss rate is getting improved. In order to improve the cache performance, there are a number of ways to do that, and one of them is a multiple levels of cache. So there is a level 1 cache and level 2 cache between the processor and memory. And typically level 1 cache is inside the CPU, and level 2 cache is a larger size. It is off chip. Another cache performance, another way to improve the cache performance is instruction cache and data cache separation. Well, instruction cache is a special characteristic. It usually have a greater locality because if you think about the instruction sequence, instruction execution, usually they are executed in sequence, and if there is the loop operation, for loop, while loop, that's typically the spatial locality. So there is an abundant locality in the instruction rather than data. And also, instruction cache doesn't need to support the write operation. It's just a read only, because you don't, I mean, program doesn't really change the instruction at runtime. So by just utilizing those special characteristics, you can optimize the instruction cache, and that's how we improve the cache performance. And associativity is another great way of improving the performance. We are going to discuss in the next slide. But if you look at the performance chart, the miss rate is improved by increasing one-way, two-way, four-way, eight-way. I mean, extreme case is called a fully associative cache. So definitely this is something we need to take a look. And just to give you an idea, one way is direct mapped cache we have discussed so far. So this is a one-way or direct mapped cache, meaning that for the green colored memory block has the only one way, one place in the cache, right, which is also green colored. So there are actually 4 green colored blocks in the left hand side, and they are getting into try to get into the same block in the cache. So for example, D6 is let us say miss, since it is initially empty, and 5-8, unfortunately this is also the green colored block. So the recently the accommodated D6, the block has been replaced with a 5-8 block. And unfortunately, the next memory access is a D8, which has been recently eliminated from the cache. So the first 3 memory accesses are all cache misses, although D6, D8 is just in the neighborhood. That is kind of a disadvantage of the one-way or direct mapped cache, which is called the thrashing problem. So, for example, Xi and Yi map to the same blocks. I mean, the green colored block, for example, it is killing it with each other, and the hit ratio suffers. So, for that matter, the alternative cache organization or cache placement policy have been developed. So, just please take a note of the color coding of the block. It is all yellow, which means that any a memory block can be placed anywhere in the cache. For example, the first memory access D6, it is copied into the first block in the cache because it's available. And the second memory address 5-8, you can just bring the corresponding block into the second block in the cache, because you can place it anywhere in the cache, right? So, but the tag value, you have to, the tag value must be 4-bit instead of 2-bit. So because, you know, you need to remember the first 4-bit of the memory address. So the D8 in this case has not been replaced. So the third memory access, the D8 is going to be a hit. So that is the advantage of the fully associated cache compared to the direct mapped cache we discussed so far. So two-way set associative cache is more like in between the fully associated cache and direct mapped cache. So instead of 4 different colors, or instead of one single color, we have 2 different colors. So for example, D6 is it's missed. You accommodate into the green colored block. On the other hand, 5-8, you can accommodate to the green colored block in the cache, but you know, in that set, this is called the set. In that set, there are 2 green colored blocks in the cache. So although the first and second are the cache misses, the third one, D8, is going to be a cache hit. So this is called the two-way set associative cache. So in other words, in every set, there are 2 blocks in the cache. There are 4-way set associative cache, 8-way set associative cache, and so on. So again, going to the cache performance chart, typically if you increase the associativity, you have a better cache performance. So the fully associative cache, you can achieve the best performance because it's the most flexible placement policy. So what is the problem with the fully associative cache if it is such a, it just shows such a, good performance? First of all, it's a complexity and slow. So whenever the memory address D6 is given, CPU is decomposed into two parts, tag and offset. Note that there is no index part. So the tag value 1101 is going to be compared to all the tag value in the cache. So since that particular memory block D0 to DF can be placed anywhere in the one of those 4 blocks in the cache, you need to compare with all of them. So which means that you need the 4 comparators, which means that this is more expensive. And consider a realistic example of the 1024 cache blocks in the cache system, and you actually need 1024 32-bit, 4-bit comparators. So that's going to be more expensive and also slow down the performance. So the performance, the miss ratio is going to be best, but it's more expensive and slow. Another issue is a replacement policy. In direct mapped cache, no replacement policy is necessary. You can make an analogy with a seat at a concert hall. You are given the seat in a concert hall, and you go to the place, and if someone else is sitting there, you can just ask him to leave because that's your seat, right? So, you just don't need any replacement policy because this is just so obvious. On the other hand, in fully associative cache, you can consider it as a seat at the McDonald's. Whenever you go to the McDonald's, you can you can sit any place in the McDonald's store. If it is a full, maybe the store owner is going to give person who is sitting there for hours, ask them to leave, right, in order to accommodate the new customer, which is rude, but this is more like considered as a least recently used or LRU policy. So someone is just sitting there for the longest time, you just ask him to leave in order to accommodate the new one. That's going to be the fully associative cache or set associative cache. So for that matter, you need to keep track of usage of blocks. Which cache block has been there for a longest time. So that's unfortunately is not so much straightforward to implement. The idea looks simple, but implementation is not that simple. So just to give you an idea, the Intel CPU, it has 3 levels of multi-level cache. The level 1 cache is an instruction cache, data cache is separate. Level 2, level 3 are combined cache, and 32K byte, 32K byte, and the level 2, 256K byte, and level 3, 8 megabyte. And they are using 4-way, 8-way, and 16-way set associative cache. In case of AMD CPU, level 1, there's I cache, D cache separated, 32K byte, and they are using 2-way set associative cache. And level 2, 512K byte, 16-way. Level 3, 2 megabytes, 32-way.